Hello, and welcome to today's webinar, Connected Car, Cutting Edge Research Aimed at Implementing Connected Car and Driverless Car Technology, brought to you by GPS World Magazine and our sponsor, u-blox. I'm Bethany Chambers from North Coast Media, Digital Operations Manager for GPS World, and I will be your event manager today. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and will be emailed to you tomorrow. At this time, I'd like to acquaint you with ways that you can participate during today's presentation. Please notice the Submit button in the lower left-hand corner of your console. If you have a question, type it in the text box at the bottom left, and then click Submit to place your question in queue. We encourage you to ask questions throughout the presentation. We will address these questions at the end of the presentation during the Q&A portion. If you experience any technical difficulties during today's event, you may select Help using the yellow question mark button for a page of frequently asked questions, or you may use the Q&A box to submit your issue, and assistant producers Joelle Harms or Ennio Gallucci will personally assist you. Our Twitter feed is placed on the right side of your screen. You also may use hashtag GPSWorldWebinar to submit any questions during today's webinar or to enter into discussions with other attendees. You may learn more about our speakers by viewing their bio, photo, email, and Twitter handles in the upper left-hand corner of your console. If you are logged into your social media accounts, you can even share the webinar's title, description, and URL with your friends or colleagues on popular social media sites, all using the Share This widget on the left-hand side of your screen. Finally, throughout this presentation, our speakers will reference websites and resources, and you can visit those for more information. You have direct access to those links by clicking the green list icon at the bottom right-hand side of your dock. Now I'd like to turn today's event over to our moderator, GPS World editor and publisher, Alan Cameron.
Thanks very much, Bethany, and welcome everyone around the world. It's 10 a.m. in the Pacific Northwest, 1 p.m. U.S. Eastern Time, 7 p.m. in Europe, and I see we have attendees from other parts of the world as well. Welcome. Today's webinar, we're going to hear from 4 speakers coming at the connected car topic from various angles, but all within the supply stream, the supply chain of vehicle manufacture, design and manufacture. I will get to them very shortly. I just want to mention that it's Chaminda Basnayake from Renesas Electronics, John Kenney from Toyota InfoTechnology, Nick Papadopoulos from u-blox America, and Roger Berg from DENSO. u-blox is a sponsor of our webinar today. And without further ado, I'm going to turn it over to Chaminda Basnayake. Chaminda, take it away.
Thank you, Alan. So I'm going to talk about some safety implications of V2X technology and recent developments. So let's get started. So basically, for all safety applications, we need to identify objects around the car and classify them and track them, and basically establish a safety bubble. That's the idea of any sensor-based safety application. So objects are detected and they are relatively positioned with respect to the car, and that we will be limited by the sensor horizon, type of object, and any conditions blocking the view. So I've shown here a combination of how that safety bubble may look like for a car. So you could have multiple sensors like multiple radars, LiDARs, and cameras. And compared to these, V2X has many advantages. So among them, V2X can potentially have the longest range, the blue bubble that I've shown outside. And V2X can work with non-line of sight as well. Compared to that, radars, as you know, has to be line of sight. And another key advantage is that information sharing is possible through V2X, which is not possible with any other sensor. For example, if you're using a camera, you can observe whatever is happening with the traffic light, but you don't know what's happening next. Whereas with V2X, the traffic controls can broadcast face information, and that will enable others to anticipate what's going to happen next and when. So US DOT, they've done studies to figure out how much benefit we can gain out of the connected vehicle technology, and the estimate is that about 80% of non-impaired crash types can be positively impacted by V2X. So it's very, very significant. Some challenges for sensors. Obviously, any object blocking the sensor view can create problems for a vehicle. For example, if the vehicle has to observe an exit ramp, assigned to an exit ramp or a traffic light, if the view is obstructed by another vehicle or something, that can potentially delay the reaction, add more delay to reaction time. So that could be a problem. And then sensor limitations, things like lighting conditions, rain, snow, fog, any of that can create problems as well. And typically we address these by doing sensor integration. Another one would be predicting driver or pedestrian behavior. While there are rules for like merging, exiting, or dealing with a stop sign, we always use, we observe conditions and react as human drivers, but for completely sensor-based approach, this is a challenging thing. So V2X can address all of these limitations. So at Renesas, we've put together several demo vehicles, which include traditional sensors as well as V2X technology. It's an integral part of those vehicles. We can demonstrate V2V, V2I, and V2P pedestrian safety applications, and we use dedicated short-range communications, and you will hear more about this with other speakers later. What we have in the car is compliant with all the applicable standards, and again, you will hear more information later in the presentation. Compliant with all the latest standards, and the industry-wide expectation is that there will be a mandate for connected vehicle technology in the U.S. Within the next few years. So again, I think this will be discussed in more detail later on. So what is shared over the air? Here's an example for all the passenger vehicles. It's called the basic safety message, BSM. So all the passenger vehicles are supposed to broadcast a message similar to what I've shown here. Not all the information are included. For example, the cars will have to broadcast time, position information, and position accuracy, for example. And then it also includes motion information, speed, heading, acceleration information, as well as some control information, so that others can predict the behavior of another car. And for this audience, I think GNSS data will be another significant component. So optional data, we can include optional data from a vehicle, like correction data or row measurement data in RTCM format. That's another feature we added to these standards. So this message is defined in SAE J2735 DSRC message set, and I think John will cover more details of this later on. So in terms of basic concept of operation, the idea is everybody will be talking to each other. Everybody will be aware of each other. So any car will be broadcasting, passenger vehicle will be broadcasting BSMs, and pedestrian or personal devices will be broadcasting an equivalent message called personal safety message, PSM. And then all the control devices, like traffic controls, they're supposed to broadcast signal phase and timing information, stat messages, intersection map, and optionally GPS correction data. So the idea is everybody will be aware of each other, whatever is happening in real time. So from the host vehicle perspective, each vehicle is supposed to be able to classify all the other communicating vehicles and pedestrians to see if they are a threat or they are significant for the host vehicle. So all the other vehicles will have to be classified as traveling in the same direction or opposite, same lane or not. And for the host vehicle will have to know which road it's traveling in, which lane it's traveling in, and even where in that lane. For example, for vehicle to infrastructure applications. In general, two accuracy levels are defined. Road level, better than 5 meters. Lane level, better than 1.5 meters. And the application requirements will be different. For example, EEBL, emergency electronic brake light, will require only road level accuracy, which means basically saying somebody in front of you is braking. Whereas FCW or forward collision warning, it's very specific. It says basically somebody in your lane is braking, so you got to brake. So it depends on the application. So in terms of what applications are out there, there's a lot of applications out there. A good source of that is this connected vehicle reference implementation architecture site. This was put together through US DOT-sponsored research, and in there you can find various applications classified into different types and functional groups. So safety, environmental, support, and mobility are the 4 main categories. And I've included a screen capture of the V2E safety function category, and the EEBL is one of them. So I encourage the audience to go there and take a look at all these applications. And then in terms of what's happening with US DOT, the next important thing that's going on right now is this connected vehicle pilot program. City of New York, Florida, and Wyoming, they are going to deploy some of these safety applications in selected vehicle fleets. So that's going to be a very interesting next step for V2X deployment. Here I'm showing a closer look at the EEBL application. So if you look at that site, you will see these sort of functional diagrams basically showing that the vehicle OBE or onboard equipment talking to another OBE over the air, and then how the host vehicle OBE interacts with the driver and vehicle data. So there's a lot of information there about these applications and their functionality. So when these applications were prototyped and developed, a lot of research went into this, DOT-funded automotive OEM research. Some of the things these consortiums looked at are like positioning technologies, what's out there that we can use. Almost all the systems out there today are using GNSS as the time and positioning sole source, simply because it's available anywhere, anytime, and it's standalone. And as you all know, there are limitations. Sky view, for example, reflections, multipath, and so on. So typically, all the systems that's out there today are using GNSS and INS integrated. And again, I think you'll hear more about these in a later presentation. So in general, the expectation in the system design is that all vehicles will provide position information and like location and location accuracy estimate. So a vehicle device should be able to get this information from itself and from others. So the idea is each vehicle should be able to relatively position everybody else, and then with the onboard device, the vehicle should be able to position itself with respect to the roadway. So as I mentioned before, there was significant research that went into this over the years, and I've included several references here, several GPS World publications, and one publication from CAMP, which is Crash Avoidance Metrics Partnership, which worked on prototyping these applications from around 2002-2003 timeframe. Typically, the challenges we have are we need to optimize the over-the-air data volume. We can't broadcast everything out there, so we have to minimize the volume of data that we send over the air, but we have to have a balance between that and application functionality. And as you all know, the other challenge is urban environments. We can have sky view limitations, rapidly changing sky view, and Of course, in terms of implementation, there'll be vehicle implementation, hardware differences, as well as user type differences. For example, a pedestrian device is very different from a vehicle device. So these are challenges that we are still working on as the industry. So finally, a slide about what was envisioned when we thought about relative positioning. The concept was to use some sort of correction data. It could be an intersection. It could be any other correction source. Use that information in a vehicle to get better position accuracy. Of course, we can do road level applications with standalone GPS, GNSS, but for lane level applications, we would need some additional corrections and better positioning for better accuracy. So that brings us to the end of my presentation.
Thanks very much, Chaminda. We're going to hear next from John Kenney at Toyota InfoTechnology, and John's going to talk about some choices coming up for the connected car environment. As in any industrial development, there are choices, and in particular, some of these concern spectrum. John, take it away.
Thanks very much, Alan, and thanks to the GPS World crew for putting this together. So the title of my talk today is V2X Status, Standards, and Choices, and what I'll do is talk about the status of standards and deployment first, and then I'll get into a couple of issues that are hot today with regard to how we're going to use the spectrum in the U.S. and in other parts of the world with regard to what kinds of technology to use to support V2X, and also on whether or not that spectrum can be shared by other technologies for other purposes. So I'll start with this diagram that shows the DSRC protocol stack, if you will, and the key standards that support DSRC. The ones that are in green of one shade or another are all designed specifically for DSRC, but we also see in the gold color that DSRC can support internet protocols and internet applications for those cases where that's a more appropriate choice. I'm going to concentrate a little bit more on the DSRC specific standards, though, in this talk. So working from the bottom up, we have something called IEEE 802.11p, which is the foundation of DSRC. It's a variation on the Wi-Fi protocols, and it defines our physical and medium access control protocols, and they're very, very similar to normal Wi-Fi with a couple of key differences that make them work in the high mobility, high speed vehicular environment. Then we have a set of standards coming from a group called the IEEE 1609 working group that define how we can use multiple channels efficiently, how we would define a lightweight network and transport layer protocol that we call the Wave Short Message Protocol, and how we can do security, including authenticating messages and encrypting messages where appropriate. And then up here in the upper left-hand corner, we have a set of standards coming from SAE, and Chaminda has touched on this already. One standard that is SAE J2735, which defines message and data formats for over-the-air transmission. And then another emerging standard is J2945, which defines rules for how you use these messages to accomplish certain applications. One important milestone was that last year we went through a concerted phase to update these standards so that those that would be important for the pending NHTSA mandate for V2V safety would be ready for NHTSA to reference in their regulation, which we expect to be published very, very soon. So last year was a big effort toward basic safety message standardization and getting everything up to date for that. And by the way, there's a reference at the bottom of this slide if you're interested in a little bit more tutorial, deeper treatment of this topic. So that was where we were last year. This year, SAE is continuing its work and kind of moving on beyond the basic safety message and taking up a number of other topics that allow us to to fulfill the whole mission of DSRC. We have various task forces that we've set up to deal with V2I and additional V2V safety issues, but also V2 others, including pedestrian safety that Chaminda mentioned with the new personal safety message, a task force for cross-cutting issues, and a task force on introducing communication to help the automated driving function we call cooperative automation. And this is where things like cooperative adaptive cruise control and platooning will be addressed. So SAE continues to be very busy advancing new standards for DSRC. A quick comparison with where things stand in other parts of the world. In Europe, the technology is quite similar and standards are also quite similar. It's all based on the same 802.11p based PHY and MAC. The spectrum is the same, a similar level of maturity. The main difference we see in Europe is that whereas we're looking to jumpstart deployment with this NHTSA V2V mandate, they're looking at more of a voluntary model with a mutual commitment among the automakers, and that leads to some slight differences in points of emphasis to show more day one benefits and to put a little more emphasis on V2I and a little bit less on V2V compared to what we're doing. But overall, it's a quite similar situation. In Japan, there's also a lot of similarities, but there are also some differences. Instead of using the 5.9 gigahertz spectrum, they're using the 760 megahertz spectrum for their primary V2V safety exchanges. And they also have additional spectrum in the 5.8 gigahertz band for other safety and other ITS types of exchanges, but these are primarily I to V. One important note is that the deployment has already begun in Japan of this system called ITS Connect in the 760 megahertz band, and Toyota began this late last year, and by April of this year, there were already more than 40,000 vehicles equipped with this technology on the roads in Japan, and we're expecting a rapid ramp up there as well. So let me contrast this DSRC standardization with some emerging standardization coming from the cellular world. 3GPP is the main standards body there, and they're now working on something that they call Cellular V2X, which is divided into a nearer term LTE V2X and a longer term 5G V2X. The LTE V2X is in the initial standardization phase now and will be part of release 14. And the 5G discussions overall and 5G V2X more specifically are now starting, and they're starting to look at use cases and requirements. Standardization efforts will ramp up probably next year and the year after that and the year after that. 5G is a more complicated thing because there are really many facets to it, and so there could be one part that's more of just an enhancement of the LTE V2X, but there can be other parts that are more fundamentally different and moving, for example, into the millimeter wave band. So one question, and this gets us now into the choices part of the discussion, one question is, how do we think about this emerging cellular V2X, and in particular, should it be viewed as a possible substitution for, as a competitor for 802.11p based DSRC? And we're seeing in some discussion forums and in some comments in standardization bodies that there are certain companies that come from the cellular world that would like to think of it that way and are trying to position it that way. But I can tell you that if we look at who's supporting it, one thing you notice right away is that this is not something the automakers are behind. Now, of course, I don't speak for all the automakers, but I do talk to my friends frequently, and I know that we're really committed to making this 802.11p based DSRC work and getting it into full deployment and reaping those benefits, especially safety of life benefits. One thing to consider is that while they're working on initial standards at this point, that in some ways puts them at the point where DSRC was more than 10 years ago when initial standards were being developed there. And what we found is that standardization is necessary, but there are many other stages that are important as well, including feasibility and small-scale testing and large-scale testing and product design. So we may expect that this cellular V2X won't really be available for deployment in a way that automakers would consider for many years to come. Another point to consider is that that the nature of V2X communication is really fundamentally different than what we're used to in the cellular world and in the Wi-Fi world, where with access points and base stations, we have a built-in infrastructure to mediate different technologies, and so we can do quick evolution from one generation to another. But V2X is an inherently ad hoc network, and that makes evolution from across generations a much more challenging task. So we really have to make a choice and then have some discipline to stick with it. And in the case of DSRC, we have made that choice. It is going to be 802.11p based, at least in Japan and Europe and the US, where those deployment plans are mature. Other parts of the world, maybe they're not so far along, and they might make different choices, and that's fine. But the conclusion that I want to pass along today is that for these markets, Japan, US, and in Europe, we should consider the cellular V2X as complementary and not as a competitor to 802.11p based DSRC. It can do things that maybe DSRC isn't already doing, for example, operating over longer ranges or in the millimeter wave band. And I want to switch to my last topic here, which is spectrum sharing with Wi-Fi devices. This is a really detailed topic, and I won't be able to go into it in any kind of real detail today, but I just want to kind of set the stage because a lot of people are talking about it today. The basic question is, can technologies like Wi-Fi or other unlicensed technologies share the spectrum that DSRC would be using without causing interference? So on this slide, we see a diagram of the band plan for DSRC, and channel 172 here is quite important. This is where the basic safety messages will be sent. Channel 176 is where the personal safety messages for pedestrian safety will be sent. And channel 184 is where some emergency vehicle exchanges will be sent. And these other channels are where all of these other applications that Chaminda mentioned are going to be using, including for safety and non-safety purposes. So what we've seen coming from the Wi-Fi community are a couple different ideas about how sharing might work. One idea that's called detect and vacate is pretty simple and looks like it has promise. This diagram on the left shows how it would work if you had a Wi-Fi device. Now it would have a DSRC detector built into it. And even if it's next to a road, if there happen to be no cars on the road, then it doesn't detect DSRC, then the Wi-Fi could use that 5.9 gigahertz band. But over on the right part of the screen, when cars are present, the detector would detect them and it would shut down the Wi-Fi network in that band and move it to another band. So it's a pretty simple detect and vacate idea. By contrast, the other idea that's been put forward is called rechannelization, and it calls for really some fundamental changes in how DSRC works, not so much on the Wi-Fi side, but on the DSRC side. So they want us to move our safety communication. They want us to change our channel bandwidths, and I'll leave it at that. But I'll give you a sense of what our response has been from the automotive community. We've been saying for 3 years now that the detect and vacate has potential and should be tested. It looks like it might work, but we're fundamentally opposed to this idea of rechannelization. There's a link here for a more detailed critique of that if you're interested in seeing what that is. So to begin to wrap up, on the spectrum sharing issue, the current status is that the FCC recently issued what they call a public notice, and that public notice asks for comments on these two sharing ideas, and it also sets out a schedule to have the FCC coordinate testing of prototypes that would be supplied basically between the end of this summer and January. Personally, I think that that's probably too aggressive. I don't know if we can do the rigorous testing in that short period of time, but we'd like to see it move ahead as quickly as it can. Comments will be due on July 7th, and we'll see a lot of those coming. And the basic position from the auto industry is that we want to remove the uncertainty that's hanging over our head with this sharing, but only in a way that rigorously protects DSRC's safety of life mission. So if I can just wrap up and summarize, DSRC technology is now mature and it's entering the deployment phase. The cellular V2X technology that's in the initial standardization is interesting. It offers benefits by complementing DSRC, but we don't want to see it positioned as a competitor. And finally, DSRC should be allowed to use the full spectrum for the safety mission, and sharing that doesn't threaten that mission should be permitted. That's sort of the consensus opinion, I think, in our industry. And with that, Alan, I'll be glad to turn it back over to you.
Hi, Alan. I think you might still be on mute.
Thanks, John, for that presentation. I've learned a lot during the last two presentations, and I think it's fair to say that we will recapture a portion of the webinar in an upcoming issue of the print magazine. We're going to hear next from two suppliers in the automotive manufacture, design and manufacture chain. First, from Nick Papadopoulos, u-blox America. Nick, the floor is yours.
Thank you, Alan. Good morning, good afternoon, good evening, everybody. I'm going to spend a little bit time on the various options of connectivity, either functional or safety related, and also go back a little bit to what my colleagues Chaminda and John already mentioned, to go a little bit deeper in there. For those who don't know u-blox, we are a Swiss company. Swiss not because of tax evasion or tax issues, but rather because it is really a homegrown Swiss company, listed on the Swiss Stock Exchange with over 700 employees. We are a healthy company, and I'm not saying that for bragging reasons, but rather to actually underscore the fact that we are a stable company, and as such a very good partner for the automotive industry. The core technologies that we provide are in the positioning space, in the cellular communication space, and of course in the short range space, as I said, both in the safety and in the convenience infotainment space. From the technology perspective, we started out as a GNSS company, positioning company, and expanded that first into the cellular side, LTE, 2G, 3G, and more recently into the Wi-Fi, Bluetooth, as well as the V2X space. The types of applications that our technology is used in and will continue and expand it to be used in are in the traditional navigation and traffic data, and now also the hands-free telephony, the entertainment or infotainment systems, as well as telematics services, external hotspots with respect to communicating, obviously, into the garage or the shop when the vehicle is pulled in for servicing. Then again, era GLONASS with respect to the safety. In-car hotspots as part of the convenience functionality that luxury car makers actually offer, and ADAS as part, as a predecessor, a precursor, if you will, to autonomous vehicles. This is a recap of the type of product that we do offer on the cellular side. Obviously, depending on the geographic area, LTE based. As you know, in North America, LTE is becoming more and more prevalent, with 2G actually disappearing and 3G on the way out. Other regions, of course, do depend very heavily on 3G and 2G communications. On the Wi-Fi, Bluetooth, either the infotainment side through an ME, Ella, Jody, or through the V2X side through a Theo module. And then on the positioning side, Chaminda mentioned that briefly already, on the GNSS side, based on dead reckoning for infotainment and navigation, and then going down to lane level accuracy for autonomous vehicles and assisted driving. Very important for us, and I'm sure also to the entire automotive industry, is the fact that we do have secure platforms that do offer methods to protect against anti-spoofing on the GNSS side, as well as anti-jamming, accidental or deliberate. And of course, from a quality perspective, we want to make sure that those cars and vehicles actually operate in very harsh conditions. As I mentioned also, the functional safety is a very big aspect of where we are working, both with respect to lane level accuracy positioning as well as communicating, as Chaminda mentioned, from vehicle to vehicle and from vehicle to infrastructure. And then from a cost perspective, we want to enable our partners to actually write their application on the CPU of the basebands on the cellular side, which is why we're introducing the uCPU enabled smart modem. Now let me go briefly into the GNSS side. GNSS, of course, has been around for a while, especially for navigation. The idea now as part of the advanced driver assistance systems, ADAS, and then as the next step with respect to autonomous vehicles, the lane accurate, and this is now absolute position, is key. Relative position is important, but if usually tectonic shifts do not occur overnight, so absolute positioning is actually a very fundamental feature and function that is required by such a GNSS-based system. And the required, of course, is not only about the position, but also with respect to velocity and heading. The reason behind it is, of course, that system, positioning system, would work under all conditions. Does not need or require any landmarks because cacti in Arizona actually do tend to move. We do not rely necessarily on that visual positioning at all. And of course, it allows us to create crowdsourcing of maps. Here's the idea that we have with respect to a requirement for autonomous driving. In open highways, but also in urban highways, we do expect and want to achieve a sub-meter accuracy level 95% of the time, which means that in an urban canyon, you do still have the possibility to have a better than 1 meter accuracy that puts you smack in the lane. You can imagine, depending on the type of vehicle, you're talking about an accuracy that is a fifth of the length of a car. So all of a sudden, the geometry of the vehicle actually may play a role here in order to avoid a collision. And of course, because of the speeds involved, you need to have a positioning update, a true positioning, calculated positioning update rate of better than 10 hertz. So you have an updated position, velocity, everything, heading every 100 milliseconds. The idea, of course, is behind you have autonomous vehicles driving around right now, as you have read, I'm sure, in the media or heard in the media. But the idea is that that we actually make this possible on an affordable scale, rather than having to pay $100,000 to equip every vehicle for that. To Chaminda's point again, the integrity of the accuracy in absolute terms is key. So it's one thing to know where the vehicle is, I as a driver. Another thing, what the positioning technology provides for a position. You see that here in the spot in the middle, and the so-called protection level, which actually identifies how accurate is the position that you are currently seeing, you being the car. And we actually tackle both those items, both the position and the protection level. And again, under all circumstances, whether it's in multipathing or poor visibility of the sky. How do we do that? We have about 20 years, 19 years worth of know-how in positioning technology based on GNSS. But over the course of those years, we obviously have developed multiple technologies to complement the purely satellite-based positioning. And you see here the various technologies that we already have in-house. We are selling today products that actually do offer those various technologies and various products. And the key for us was now to actually combine all those technologies into a singular solution that actually works with multi-constellation systems, be it the American GPS, which is the pioneer, of course, then the Russian GLONASS, the European Galileo, the Chinese Beidou, the Japanese QZSS, and so forth, and allow the best position to be determined from those multiple satellite technologies. We also incorporate three-dimensional dead reckoning. Now imagine you have a stacked highway, 3 or 4 level stacked highways, and you have 4 vehicles on 4 different highways driving toward the cross point. The last thing that you want is for all those V2V or V2X systems to alert each other that they are on a collision course, which of course they're not because they're on different levels. So in this case, the third dimension actually comes into play, and the accuracy that we actually have developed for the third dimension allows for those false positives to be avoided. The other thing is multi-band. You see in red here, multi-band meaning that we don't rely only on the commercial typical L1 band, but also L5 band to be able to mitigate multipathing. And then, of course, the so-called PPP, precise point positioning, as well as real-time kinematics. This is an example of where we actually can truly identify the change of lanes. You see at the bottom the repeated track where we drove several times on the left lane. Clearly this test has been done either in the UK, in this particular case it is the UK, or Australia or other left driving countries. And the top one you see where we actually did drive from one lane, the left lane, onto the right lane. And that is something that we can very reliably track right now. So much for the GNSS, and this is actually also the reason why we very much encourage both Tier 1s and OEMs to actually keep the cellular communication technology, the short-range communication technology, and the position technology separate, because the technology advances on the GNSS and the positioning for autonomous vehicles are extraordinary and can only be done in the separate GNSS-based technology. Here you have an example of a communications device based on our Tobii L4. In the middle you see OEM VM Yocto. This is the ability, gives us the ability for customers to actually write their applications. The next slide shows also the security portion where we actually maintain the integrity of the communication side. And here is an example of an infotainment system. You see in blue here the components that we actually supply. The GNSS with three-dimensional dead reckoning, and in the future with lane level accuracy. The Tobii L4000 with the customer application, as well as Wi-Fi, Bluetooth, and near-field communications on the left side. This is again a high-end infotainment system. Whereas the next one shows an example for a low-end Category 1 LTE telematics unit. Again, the GNSS separately, and if you want V2X, you actually can add that on top of that. I will skip this slide. This just shows what we do for automotive. And this is the last one. This is the reason why our customers and partners chose us. Back to you, Alan.
Thanks very much, Nick. I see some excellent questions coming in from the audience. Obviously a very knowledgeable audience. We'll get to a few of those questions at the end of the webinar, and then we'll find a way for our panelists to answer more of the questions than we'll be able to address over the air. Do that in writing and get those answers distributed to the audience. We're going to hear finally from Roger Berg at DENSO. Roger?
Well, thanks, Alan. I appreciate the opportunity to present today and share some knowledge as well as the other three valuable subject matter experts. As the fourth speaker, a lot of this stuff will be a slightly bit repetitive, but I'll try to give you a kind of a slightly different viewpoint as well. So my talk is about connected and automated vehicles, kind of the combination of connectivity and automation. So normally I start out with a little summary of what DENSO is, because it's not really a well-known name like Toyota. We are a 65-year-old company. We're senior citizens now, but not ready to retire yet, since we have revenue of $40 billion. We're one of the top tier 1 suppliers in all of the transportation industry, with 150,000 employees in 36 different countries. And as an R&D engineer, I'm pretty proud of the fact we have over 38,000 active patents worldwide. We do this in terms of developing systems and integrating systems for customers like Toyota, Ford, GM, Honda, and maybe some of you haven't heard, like Polaris, Peterbilt, and John Deere. But anyways, our systems are in the areas of environment, which is heating, ventilating, air conditioning, comfort and convenience, which has a lot to do with climate control as well, but also more relevant to today's discussion, safety. So here's how DENSO looks at really the future mobility society. I'll go through this pretty quick. You can see it's centrally based on really a broadband connectivity between the mobility unit or element, whether it's a car, truck, bus, ride share, automated drive, not automated drive. But we're actually sharing information between the transportation system and the actual vehicle that translates people from point A to point B, people or goods from point A to point B. And I don't have time to go through all of this, but you can see is that there's many different facets that really are helped by this broadband connectivity, including automated driving. So when we talk about the connected automation concept, we're not saying that connectivity is the only way to look at, or the only function that's necessary for vehicle automation or transportation automation. We see the combination of the closer in range, the autonomous sensors around 100 meters or a couple hundreds of meters, using the traditional sensors like sonar, cameras, millimeter wave, radars, things like that. And then we move, as we look at longer range from the vehicle in terms of its connectivity, we look at what we call an ADAS locator, which traditionally uses GNSS as a way to position us either on a map or on some other localization frame of reference. And so that can help us to determine where the next turn is, what kind of road we're on, whether it's a downgrade or upgrade, or whether there's an exit or entrance ramp and things like that. So that helps us in our kind of connected automation vehicle awareness. Then we move to the V2X ECU, which is a little bit longer range, where we use this kind of horizon. And the speakers before have talked about this extensively, so I won't waste too much time on it. But we also extend towards what we call the TCU, or the telematics communication unit, which is really our connectivity to the cloud and all this information that really helps the mobility system move forward and emerge. Now, if we talk about ADAS and how ADAS extends to automated driving, we can see that the years here aren't all that critical, but what I wanted to portray with this diagram is that as we see the more complexity of these different functions, from comfort, collision avoidance, road departure, monitoring, and nighttime driving assist, as we see these functions get more complex, we see the advent of more and more different types of sensors. If you look at the little legend in the lower left, you can see these more complex functions almost get to use each one of those different sensor types. And DENSO has done research and product development in all of these areas. And so we have a bunch of this stuff already in production and are integrating it to do various levels of automation, but we're still improving on this sensor suite because it's simply just not, it's good enough, it might be good enough for a single application, but not good enough for highly automated driving. In all cases, under all environments. And so we see here that no matter, even if we're improving these sensors and improving them steadily, even so, the physics of the physics of the device really limits how it can be used. So you see here, LiDAR is really good under certain conditions for certain objects. Cameras may be slightly different and works in areas where LiDARs or radars might not. And then we see this connectivity between V2X and cellular, and this map and location where we look at space-based positioning systems. And we look at how robust they can be under different conditions. When you talk about highly automated vehicles, usually you talk about them driving almost wherever a vehicle can go. And so it has to work under rain, fog, and at night as well. But sensors aren't the only thing that are relevant for this kind of automation continuum between full driver control and full cyber control. Sensing is the point we see at the top, but really taking the data from the sensing, whether it's cooperative or autonomous, and really processing it into something that's understandable for the applications and the scenarios where automated driving or ADAS operate, and converting that into actionable information for the physical actuators, and whether I want to turn left, turn right, change lanes, stop, accelerate, decelerate, or whether I've reached a condition where I need the driver to intrude and take control because the sensor simply can't. That's all part of what we call this combination of hardware and software, sensing, processing, actuation, into what we call a cyber physical system. But let's not forget about the connectivity aspect. I mean, that's kind of here what we're here to talk about. And connectivity provides things that these traditional sensors don't. What I call like 360-degree awareness. So when you use connectivity, you can be aware of what's going on behind you if it's important. There's a car coming behind you, or an emergency vehicle. You can get data as to the state of the red, green, or yellow light when you're approaching, and whether you need to slow down and stop, or whether you can keep going to get kind of environmental or fuel savings aspects. And then this traditional cloud internet where we can get contents, maps, things like that. So I mentioned before that the traditional sensors such as radar, LiDAR, and cameras are really great for line of sight, but we think we need like this kind of multi-spectrum sensing, and in this case, we think this V2X or V2V is going to be really valuable when we step towards that edge of the spectrum where we talk about high automation. So here I want to show a demonstration of a typical scenario where a radar, camera, or LiDAR might not work. So just imagine you're in this vehicle and you're on, let's say, like a normal arterial roadway, and you're following the vehicle in front of you, and we don't see other cars because we're on a test track, but there's other cars around you, and you're really watching the guy in front of you, trying to get the right, kind of interval. And you're driving along,
hard braking vehicle ahead.
He sees somebody
Forward collision warning ahead.
But you didn't see that person, nor would your camera, radar, or LiDAR. And so in this case, this is an example of how we use V2V to take care of collision scenarios that really couldn't be helped by traditional camera, LiDAR, or radar. One of the things I wanted to mention that I only noticed during Nick's presentation is this example. We used a Toyota vehicle. You might look at the steering wheel and see the Toyota insignia. The fact behind this V2X system that's installed in this car is that it used a u-blox positional element, and a Renesas V2V module. So I thought that was kind of neat. So one of the things we've learned, or three of the things we've learned in talking about cooperative systems, and cooperative means this connectivity in addition to automation, is that not one company can do it all. We've done a bunch of governmental contracts and pilot systems and prototype deployments, and we've learned that nobody has the expertise to do all of this by itself. The second thing is no longer is the vehicle its own entity, that it doesn't operate separate from the infrastructure and other road users. It's really a cooperative system, even from the point of how the roadways are constructed. And another thing that we've learned through experience is we can't predict how connected and automated drivers will interact, or systems will interact with regular vehicles, regular human-operated. And so it's going to take a lot of collaboration, cooperation between industry, academia, and governments to be effective. So in summary, I want to conclude the future mobility society will really center around connectivity and the use of information, whether it's very localized in terms of a couple meters from your car, or regionalized, or even some global information will be important. And that a suite of devices with multispectral sensing, meaning light, RF, ultrasonic, will really be necessary for all aspects of highly automated driving, but it's really not sufficient for all scenarios. So we look at the idea of cooperative sensors such as V2X, cellular, and GNSS with connectivity to enhance the robustness of where and when we can activate this automation concept. And really, because it's cooperative, there's a lot of stakeholders, and we must all cooperate and collaborate across industry, academia, and government to enable safe and comfortable connected automation. So that's a conclusion. Back to you, Alan.
Thanks very much, Roger. I want to let all of our audience know that we are going to go a little bit past the top of the hour. We'll stay on for another 10 or 12 minutes to answer some questions, if you can stay with us. The first question is, and I think John indicated he might answer this, and if anyone else would like to join in as well. A question comes in: are there concerns with respect to the use of a relatively dated Internet Protocol standard, that is 802.11p? John?
Thanks, Alan. Yeah, that's a good question, and we get that from time to time. So let me put that in a little bit of perspective. The 802.11p amendment is one of a series of amendments to the original 802.11 standard, which I think dates back to the late 90s. But the P amendment that we did that's specifically for vehicle communication is 2010. So it's not really all that old. And what we did in that standard was we built on the legacy of Wi-Fi, reusing the same carrier sense MAC, reusing OFDM, which is a good spectrally efficient physical layer. And we added features that make it suitable for the outdoor, high multipath, high mobility environment the vehicles experience. So for example, we decided to use 10 megahertz channels instead of 20 because they are more multipath resistant, more tolerant to multipath. We decided to adopt a tighter, what's called a transmit spectral mask, to allow our channels to operate near each other without a lot of energy leakage from one to another, and also a tighter what's called receive rejection requirement for the same purpose. We also did away with the traditional access point and the delays associated with an access point because we wanted cars to be able to communicate with other devices in an ad hoc manner instantly. As soon as they're within range of each other, they can communicate. So we made all of these advances, and so that's really a quite different and quite modern version of the 802.11 standard. But the other thing is that what we're seeing is intense competition emerging from the chip suppliers and the general supplier community to differentiate their products from each other by adapting the most modern state-of-the-art features, especially with regard to receiver characteristics that are not part of the standard. So the devices that we're testing and that we're seeing and we'll be moving into deployment with have all of the latest theory built into them with regard to how to best pull these RF signals out of the air and turn them into usable information. So in a word, no, we're not really concerned about that. It's not really a dated standard, and we have a lot of modern features that are being added even outside of the standard.
Thanks, John. Would anyone else on the panel like to address that question before I move to the next one?
Not me. As usual, John's very thorough and easy to understand.
All right, thanks. Second question, how will the relatively slow update rate to the GPS navigation message be handled? And I'll just throw that open to the floor.
Can you repeat that question?
How will the relatively slow update rate to the GPS navigation message be handled? And when this questioner says relatively slow, of course, the emphasis is on relative.
Well, I don't know that the 10 hertz update rate is actually really that slow with respect to positional updates. I think the general direction of this question is more toward the traditional GNSS perception, as in, you have 1 hertz or 2 hertz updates. Here you have now a 10 hertz update with a true position within 1 meter. So I suspect that this should actually be sufficient. At least we believe it should be sufficient for autonomous cars from a safety perspective.
Terrific. Thank you.
I'm not sure if, Alan, is the question about the GPS navigation data message itself, that's broadcasted out of the satellites? Not sure.
It's not clear from the context of the question.
Okay.
All right, I'll go on to our next question regarding multiband reception. Which second frequency is suitable for the consumer market, L2C or L5? And a question for you, Nick, does u-blox have a plan to bring up dual frequency GNSS solutions in the near future?
It is our belief that L5 is going to be the better choice for multipathing, and the answer is yes.
Yes, you'll bring a dual frequency capability into V2X. Is that right?
That is correct.
Terrific, terrific. Well, I'm going to draw the webinar to a close. We have several other questions that I will circulate among our panel, and we'll get a written transcription of them out to the audience. And as I mentioned earlier, look to see some of this content in the August issue of GPS World. I'm Alan Cameron, editor of GPS World, and I'd like to thank Chaminda Basnayake, John Kenney, Nick Papadopoulos, and Roger Berg for their participation in today's panel on the connected car. And I'd like to thank you, our audience, for attending. Bethany, back to you.
Thanks, Alan. And thank you to our audience for attending today's webinar, Connected Car, Cutting-Edge Research Aimed at Implementing Connected Car and Driverless Car Technology, presented by GPS World and our sponsor, u-blox. Before we close out, you can access the resources mentioned today, including a PDF of the slide deck, by clicking the green list icon in your dock. If you have further questions, feel free to reach out to our speakers using any of the links in their bios on the left-hand side of your screen or in the emails that are on the screen right now. A recording of this webinar will be posted to our website and will be emailed to you tomorrow. If you want to bookmark our webpage now, just click the GPS World logo in the bottom right of your screen. Our next webinar is coming up in mid-July. Registration will be opening soon, so please check back at gpsworld.com/webinars to sign up. Thank you for attending, and we hope to see you at a future GPS World event.